In this lecture, we'll cover some additional details on the foundations of foliation theory, as well as the definitions necessary for holonomy that were not covered in the second lecture. In particular, there are some technical stuff that in the physical version of these lectures became a little bit confusing for members of the audience, and so I wanted to address and clear up some of those concerns for anyone who might want to see the more rigorous underpinnings for what's happening. So the primary source for what I'll be covering here is Kandel and Conlon's book, primarily sections like 2.2, 2.3, I believe is what it is, on the introduction to holonomy. Additionally, Danny Caligari's fantastic book on foliations and the geometry of three manifolds influenced a lot of the way I want to present this and the topics I care about in three manifold theory. But as far as following along with readings, Kandel and Conlon is certainly the way to go. Okay. So the first thing I wanted to mention is kind of what is, a little bit more formally, a product chart. I'm still not going to get into the super formalities in this video. There will be very few proofs and very few like super set theoretically rigorous definitions. It's just to give a little bit more of the idea for what's going on, so that you can then go and read Kandel and Conlon and hopefully follow along pretty easily with the proofs and the definitions. But the idea is that we start with some foliation, and you'll have to apologize for the bad handwriting here. But we have some foliation here given in green. And then on top of that, we have a box neighborhood, this white thing. And the white thing should be kind of bent. It's not drawn this way, but it should be bent in such a way that when you take the box neighborhood and you take the foliation and you map them over to Rn, the box chart just becomes a nice like n-dimensional rectangle. And the foliation becomes horizontal planes. So formally it becomes like the box becomes a local copy of r to the n, and the green things become r to the k's embedded in a flat parallel manner inside of that. So it should be r to the n in total, and then in the vertical direction, in the horizontal direction we'll have like r to the k, the vertical direction will have r to the n minus k. And it should be in the way you would expect, where we just set some of the coordinates to be 0 in order to embed this in the natural flat way. Okay, and so this is called a box neighborhood or a product neighborhood. You see a lot of terms for this. So once we have that, we really need to talk about what happens when you have two of these things, because these are supposed to be akin to an atlas, to charts you would get on a manifold a priori without any foliation. We just kind of want to upgrade them to now account for the foliations as well. So when we have two charts that overlap, here I've drawn that with these red leaves, we need this so that when you straighten it out, it basically gives the picture to the right. It should be that wherever these charts overlap, it basically exactly looks like the overlaps are, what's the best way to say this? That these are, it almost looks like you have like a new box neighborhood coming from the overlap, if that makes sense. It should be that you just start on a plaque of one chart, you move over to the plaque of the other chart, and wherever they intersect, exactly has the plaques overlap in a one-to-one manner. So you don't want plaques meeting at angles, for example, where you could have one plaque coming in from one intersect multiple plaques from the other. They need to globally glue together to form a leaf. So they'll largely all look like this picture. We could have something a little bit more weird. There's a picture of this in Kandel and Conlon, where maybe we could have a leaf spiral around, maybe a little bit like that. But wherever that leaf, we could have a chart spiral around like that. But wherever that chart intersects our given chart, it always has to intersect it along like these horizontal lines. So it has to be very flat and horizontal, exactly where it intersects. So I think the right model to have in your head is something like this. where it is literally just two squares overlapping each other, and it is a bunch of horizontal lines where you can go from a fiber of one on the left, one of these green things, and you literally just follow it along to the right, and it takes you into a fiber of the next chart. Note that this depends on the trivialization we're choosing. It might look more complicated in the actual manifold itself because we need non-trivial foliations. We don't just want product foliations. So it needs to be that as you trivialize in multiple different ways, it might locally look like it trivializes just by following along to the right, but it can globally have leaves pulling apart. Okay, so this transition map we define, which is akin to the transition map you normally have for transitioning on a manifold in charts, is called the holonomy cocycle. And our charts have natural x and y coordinates. X coordinates going horizontally, y coordinates going vertically. And because we need to line up each of these leaves, each of these plaques between charts, each plaque corresponds to a specific y coordinate. So it's like we're taking one y coordinate and turning it into a different y coordinate, because they could have different coordinate systems, but we need them to glue together. So that's all this holonomy cocycle does, is it takes one y coordinate to another. Some authors will have this as gamma alpha beta, some would be gamma beta alpha, depending on which way the author thinks about it, taking in entries. There's a chance I actually got this backward from Candel and Conlon, but hopefully the idea should be clear there, in that it transitions from one chart alpha to another chart beta, or vice versa, depending on the convention. So importantly, these holonomy cocycles, these transition maps, satisfy three properties that are akin to check cohomology. So you'll remember from check cohomology, if you've seen it, that if you have three open sets, wherever they intersect, so in this shaded region here, we get something called a cocycle condition, where the most important one is this first one right here. It says that, again, I might have this backwards to the composition in Candel and Conlon, but it says that if you have one map that takes you from A to B, another that takes you from B to C, that's the same as transitioning from A to C. So geometrically, what's happening is if you go from here to here, and then to here, that's the same as just going straight across. It's essentially a commutative triangle, but geometric. So this means that our charts overlap nicely, and we don't have to worry about the paths we're taking between things. It essentially is a path invariance condition, geometrically speaking. And you can run through the definitions and check that this holds. This essentially is what makes foliations tick in the first place. So when you write down the formal definition of a foliation, you require this. The other two conditions are a bit more straightforward. The third one is that if you transition from a chart to itself, it's just the identity map, which is obviously what you'd want. And if you want to transition backwards, that's the same as just flipping. So if you transition from A to B, the inverse of that is transitioning from B to A. Okay, so there are three things I should define here, and Candel and Conlon use this notation all over the place, so I think it's good to be clear on what these objects are. So the first is, what is a foliated manifold? Well, you'll remember that throughout these talks, M represents a manifold and F represents a foliation. So a foliated manifold is just a manifold with the foliation. We can then build a foliated atlas on it. This script U right here, that's meant to represent our atlas, and it's a collection of open sets. It's our chart maps. So just like a manifold has an atlas, that's a collection of all charts, so does a foliated atlas contain a collection of foliated charts. And a foliated chart is just a open set with coordinates x, y that maps like we drew up above in this. So this first picture was of a foliated chart. And then we build our foliated atlas by ensuring that we get transition maps where all of them play nicely with the cocycle condition. And if we have, just like on a manifold, where if you have some regularity condition on all of the chart maps, You say that your atlas, or even or then you'd say your manifold, has a certain regularity. So that could be like C0, C1, C infinity, C omega, aka real analytic. And here it's the exact same thing. But there is a caveat in that on a manifold, there are only usually two cases of regularity you need to consider. There's like C, or I guess three if you have complex differentiability, but it's usually continuity you care about, and then you could have C1, but it turns out a C1 atlas you can always refine to a C infinity atlas, which you can always refine to a C omega atlas, and then you could have a complex differentiable atlas, which is the third case, if your manifold is like even dimensional and admits one. It's a little bit different with foliations, because with foliations, it turns out you can't smooth, basically ever. C0, C1, and C2 foliations are radically different in some ways. Beyond that, things tend to be mostly the same, but we really want to differentiate between them. And by that I mean we want to distinguish the different classes of regularity. In fact, it's really usual to consider regularity conditions like C to the AB, where we get even more nuanced regularity that interpolates between the regularity classes to say very precise results. And even then, that might not be enough. Like a lot of results on foliation theory will say hold for like C1, C1 0 plus, for example, which is even more carefully interpolated between. And it's because it's so important that you cannot always smooth out foliated atlases the same way you could with manifolds. Okay, so a foliated atlas, to be clear, when you want to actually work with foliated atlases, you want to give a few more conditions here. These are very technical set theoretic type conditions, so I'm not going to get into the weeds on them. The only one I'll mention is the second one, which says that our cover is locally finite. And it turns out you can always refine a foliated atlas to be regular. In fact, you can coherently refine it. You can read the details on this on Kando and Conlon, but you don't need to worry about it because we can always do it and just assume we have a regular foliated atlas to start with. One technical advantage of that we're going to use in this talk is that if we have a foliation with a given codimension, associated to each open set in this foliation, we can choose a given transversal, like S sub alpha is how I'll write it. So we're going to index our open sets in an atlas with this letter alpha. So U is the name of the open set, and it's indexed by alpha. So in U sub alpha, we have a transversal S sub alpha. And locally, that's just choose a vertical line in a box neighborhood. If I choose this red thing to be a transversal, there's a transversal for our box neighborhood. And it really doesn't matter which vertical line you choose, all of them will be a transversal. The theorems will all hold. You just need to have a transversal for every box neighborhood. So then when you have that, we can glue all of our transversals together. And that's a little bit important that we can do it. There's a caveat I'll mention later. But this union is called the total transversal. And if we have a codimension Q foliation, we get a Q-dimensional manifold for our total transversal. And to make sure this union actually exists as a manifold, that's where local finiteness comes in. Because our manifold is second countable, we have a locally finite collection. That implies that the number of, like the union makes sense because we have a countable atlas. So it's a countable number of transversals we choose, one for each element of the atlas, so we can talk about the total transversal as like a generalized manifold with a bunch of connected components. You can do things with like a manifold with uncountably many components where you need to be a little bit more careful. We'll come back to that. So on talking about where holonomy comes from in the first place, I should mention something called the Poincare first return map, because that's where this really gets started. There's a lot you can say about foliated bundles and the like that I'm not going to talk about, because the theory is entirely subsumed by what we'll mention. And I think the first return map gives the right intuition to start with, and then you might as well jump to the general theory, in my opinion. But if you want to see the in-between theory, where you can actually talk about like more proper groups of holonomy instead of pseudogroups, that is contained within Kandel and Conlon. But the first return map, because this is the classical thing due to Poincaré, one of the grandfathers of topology, is that if we have some flow, say we could have, so like here this flow is, it's a good color, you can see green, maybe. So we start here, and we flow around, we flow around, we flow around, we flow around. We're going to come back somewhere. So I guess the way this is drawn, we flow from, maybe yellow you can see a little bit better here. We flow down, we come around, and we flow back here. And so we start at some point y, and we end up at some point f of y. And the way we're choosing y is we just choose a cross-section to our flow. So we have some flow around a manifold, and it will form locally a foliation, and we choose some cross-section. The existence of a global cross-section here is important. It's something Poincaré approved for specific cases where he was doing first return map stuff. We will not always have a global, something globally that's normal to our foliation, so that's important. The existence of a cross-section is very particular to this case. But if we have a cross-section, then we just choose any point on our cross-section, we flow it around and see where it comes back to. And that gives a diffeomorphism. Because if we want to see where that then flows to, you just you compose it again, and you look at the first return map of the new point. And so if for every point y, we call its first return map point f of y, that builds a function that takes any point y, spits out f of y. And then if we want to find the second return, that's just f composed with f of y. Or if we want to find where it goes after time n, that's just composed n times. So it allows us to understand the total long-term behavior. This is super common in discrete dynamical systems to consider this type of thing. And in this case, this diffeomorphism f we constructed is essentially our holonomy. You can build a group out of this by talking about composition in the right way. And so our holonomy map is just accounting for like where we're returning. So that's where holonomy comes from, like originally. I should also mention there's a little bit of a caveat here in how holonomy is going to capture returns. So you'll remember from the last lecture that we draw transversals and we see where things flow to. So we could have a transversal here and a transversal here. And you, like, we can take, so let's say, let me say it this way. Let's start with this transversal and let's push it along, like let's take this bottom leaf here and let's push it along the bottom leaf. So if we push it along for some time, here it will be in the middle and here it will be at the end as we just kind of parallel push it along. And we can see that in the middle time, a lot of the leaves we started with here, they vanish. We don't see them in the transversal. So it actually ends up being an expanding map in the middle time. And then from the middle time to the end time, it's a contracting map. But from the whole time, from our start to our end transversal, it's just the identity map. In fact, if we could choose the starting and ending one to be like the same transversal by gluing together the sides of this picture, in which case we're not seeing any holonomy really at all. All leaves are coming back to each other. They might bend up really high, but then they're coming back down and coming back around. So holonomy is going to depend on the choice of transversal. That's an important caveat. When you choose a specific point on a transversal, a specific leaf, we can see some difference. So here, there's a notion of where you might say that this is, at some points, the holonomy might be expanding, some it's contracting. So we need to be a little bit precise on what exactly we mean by holonomy in this picture. So to define holonomy, we need a pseudogroup action. What is a pseudogroup? Well, a pseudogroup is something, it's a collection of functions. This is usually only defined for functions, which is kind of weird because groups don't talk about functions at all. I think it's because pseudogroups were invented by topologists. But you have a collection of functions that wants to be a group under, say, composition. But it just can't be. Not quite. So I talked in the last lecture about how holonomy is supposed to be represented by this picture here. But there are some problems. Because if we have, say, here's our function f, and here's our function g in our pseudogroup, well, first of all, we can't talk about f of g of x for every point x. Like if we talk about this fiber here going across, then, well, it's not, the image of g is not in the domain of f, so we can't compose. So the first thing is just making sure that holds. The second one is that we can always invert. So here in this second picture, we can definitely compose fibers. We can talk about f of g of x in this example. But we can't go backward with fibers, because if we start with this fiber here and trace it along backward, we end up with something that we can't follow on backward along g. So that's a problem. So we might need to restrict appropriately to be able to get inverses. And then we want that the identity map is in there, just to make sure this is akin to a group. So what this actually looks like is, I think of it as restricting and co-restricting fibers however you can to make sure that composition makes sense. So here, maybe we talk about these fibers and then these fibers and then everything in between. And that would be like what we could talk about as our composition. And then here it would be like to here, and then everything where we could follow it along. I apologize for the sloppy picture. It's hard to draw accurately on this tablet. But something like that, where we can flow forward in time and then backward in time. The last two conditions on this are some sheaf theoretic type conditions. One of them is that we can restrict, and one is that we can glue together restrictions. Okay, so the most important result here is that once we define these things called holonomy transformations, which are a certain type of diffeomorphism, a CR diffeomorphism, a partially defined one, I should mention. Like the ones up here are partially defined. It might not be defined on the whole domain of the vertical interval. Like this G is only defined for this portion of the interval. So these partially defined diffeomorphisms, called holonomy transformations we're going to define, generate, as a pseudogroup, something called the holonomy pseudogroup. And these are going to be generated over our holonomy cocycle. So we can talk about now what holonomy transformations are. This generated by the holonomy cocycle part just means that a holonomy cocycle, which remember is just our transition maps in our foliation, each one of these gives rise to a holonomy transformation. So our choice of charts gives rise to a holonomy pseudogroup. I mentioned earlier this locally finiteness condition. It turns out, so although our construction of holonomy pseudogroup here is going to depend on our choice of cocycles and thus our choice of foliated atlas, you can do this without that restriction, but you get into a little bit of set theoretic issues where you need to consider the total transversal for every possible atlas, which you can do. And it turns out the pseudogroup we're going to do, no matter which atlas you choose, all of them are going to be conjugate in this master pseudogroup, but the set theoretic issues are a little tricky to pin down. I don't even think Candel and Conlon do it. They give a note about it. But so we're going to make this depend on the atlas, but it doesn't actually need to depend on the atlas. But that requires a little bit of proof. Okay, so what is a holonomy transformation? So the part in Candel and Conlon I think is a little bit dense and hard to read right here. So I'm going to draw some pictures and explain it. So our holonomy cocycles, remember I said earlier they take plaques, so these green horizontal lines in one chart to a green horizontal line in another chart. And each horizontal line is given by a fixed y value, So you can think of a holonomy cocycle as taking y values to y values. And if we parameterize all the y values, we get a transversal. All of the y values in a given chart traces out a transversal. But the transition map doesn't take all of the y values to all of the y values. It's just the ones where you can flow horizontally and get from one chart to another. So the overlap in this picture here is just in this region. So it's only going to be the y values from, say, here are going to map to the y values here. So you can see in terms of this transversal mapping to this transversal, it's a partially defined diffeomorphism. Like if I draw out the intervals, it's going to look like we took this and mapped it like this. It is this this map. Takes the bottom half of the transversal and maps it to the top half of the transversal. Okay, so that's cool and all, but what do we do with this? Well, there's some technical details here, but the point is, to define a holonomy here, what we do is we take some points W and some point Z, which I've drawn in here, in adjacent plaques, meaning we have adjacent charts and we have plaques that join up together to form a leaf. And so we take any path connecting W and Z. Here it's one-dimensional the way I've drawn it, so there's only one path. But remember, our leaves could be much higher dimension. The ones we'll care about in this course are usually dimension 2 in a dimension 3 manifold. So you can have a lot of paths in a surface connecting 2 points. But no matter what path we choose, as long as that path lies in this picture right here, it lies in the union of the two plaques, which we think of as like a local model of the leaf in the union of these two charts. As long as our path lies just in the union of those plaques, we will define its holonomy to be the transition map. That's it. So holonomy is literally just transition maps between adjacent charts. There's nothing more complicated about it. So this whole idea of leaves pulling apart is actually accounted for already in the trivializations we choose. It's just going to be how we trivialize that will tell us how leaves pull apart. Okay. So to get a concrete idea of what that means, what this is saying is that so our holonomy, it takes in a, you can think of it as a function that takes in a, like one of the, so this, say this top green line right here. This is really two plaques. In the left chart, it's the plaque P sub U. In the right chart, it's the plaque P sub V. Together, they glue up to form the same leaf, so they should be the same. But they're actually in different trivializations. So, okay. So what can we do with this? The holonomy says essentially that P sub U gets mapped to P sub V. I think this is called like the fuzzy points in Candle and Conlon. But our holonomy transitions plaques to plaques, y values to y values. So you can think of it as either taking like a point on a transversal U to a point V, or you can think of it as taking like the whole plaque P sub U to P sub V. And that latter perspective is nice because it shows kind of how it's path independent. The whole plaque is being sent over. It won't matter which path we take. We're looking at a fuzzy perspective when we're doing holonomy. When we have adjacent, so one other thing I should mention is, so now that we had these points like W, I think I called them W and Z, which were these middle points, once we've defined that, all the holonomy does is it's basically just pushing horizontally all of the other fibers we can push. You can't push a fiber up above. Like this fiber here is not going to be in the domain. We can't push it across. But for every fiber that we can push from one chart over to the other one as the union through two plaques, The holonomy will take it from one to the other and just shift over horizontally. When you have two plaques that join together, like in this picture, so all of these green horizontal things, and you have two adjacent charts that allow you to do this, that intersect in a non-trivial way, the union of plaques going across is called a plaque chain. So in this picture up here where we just had one leaf, we have this plaque for W and this plaque for Z. That should glue together to form a leaf, and since they're adjacent to each other, they together form what's called a plaque chain. So if we have a plaque chain between two adjacent charts, our holonomy is just the transition map. So locally, holonomy is transition maps. But not every two charts in a manifold, a foliated manifold, are adjacent to each other. Some of the charts are fairly far apart. So what do we do in that case? Well, you just take a sequence of plaque chains in order to do it. So if you have 2 points that are far apart in your manifold, say we have let's give a local picture here. Let's say we have a point X, point Y. Then what's happening is we start with a chart around X, and then we just cover it with a bunch of charts that take us over to Y. So we'll have some path, and it will be contained in a bunch of charts. And going from one chart to the next, our holonomy is just the transition map. So we just transition, 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 transition until we get from the start to the finish. That's all you have to do. You choose a bunch of charts that intersect each other pairwise, non-trivially, and you just follow along the chain. You compose all the holonomy going from the start to the finish. And if we started with it, at each point we had a transversal, so we start with one for each of the charts. So we started with a transversal, we end with a transversal, and this holonomy gives a map from the start to the finish. And given a plaque chain, which using the notation of Candel and Conlon, I write with script P, we define the holonomy of that plaque chain to be H subscript P. Okay. So then to define holonomy transformations, we now have defined this holonomy of a plaque chain. So given any CR diffeomorphism, so it's a diffeomorphism for whatever regularity we want, defined on, it has some domain that lies within our total transversal S and some range that lies within it. And it might be a partially defined diffeomorphism, so it's not a map of all of S to itself. Then if this map H we find, just if we pull out of a hat any diffeomorphism, partial diffeomorphism of S, if there exists a plaque chain and a neighborhood of some point around that where we can restrict it to become, and when restricted to that plaque chain, it becomes the holonomy of that plaque chain, then we say that H itself is a holonomy transformation. So the holonomy transformations are just all of the partially defined diffeomorphisms that restrict somewhere along a plaque chain to become a holonomy of that plaque chain. Obviously, there could be multiple plaque chains where it restricts to become the holonomy of it. That's fine. As long as there exists one, that's okay. It is a holonomy transformation. So at this point, we've now defined a holonomy pseudogroup. Some authors will finish right here, and they'll say that this is all you need to do. We've defined a pseudogroup. We have a way to compose a holonomy. We have some type of algebraic structure. We're good. But really, we really want a group. We don't want a pseudogroup. We want to be able to do calculations with a group. It actually turns out in practice, knowing what the group is isn't often important, but what we really want is a representation of pi 1 into our thing, because we want to be able to use the fundamental group to do calculations. So to do that, we have to pass to groupoids. So there is this very general fact here that if you're given a pseudogroup on a manifold, and we take what are called germs of elements at points of our manifold, of our pseudogroup, those form a groupoid. So I think of this as a type of localization. we take a pseudogroup and we take germs, and that yields a groupoid. And a germ, what a germ is, if you recall, is we take some function g to start with, and we take some point x. And we take the equivalence class of all other functions, which will have the same regularity our starting function has, which agree with our function in a neighborhood of x. So graphically what that looks like is we'll have some point x, and it will lie in the domain of g, which could be this. And we might have some other function f, which maybe its domain is this. And there will be, if they lie in the same germ, there will be some neighborhood of x where f and g agree. So maybe in this, they'll agree with each other. So for any two functions in the germ, we can find a neighborhood around the point where they agree. These neighborhoods might be getting really, really tiny. So we really think of a germ as something that's happening in an infinitesimal neighborhood of the point x. If you're used to sheaf theory, this is basically a stalk. So it is like the stalk above the point x. And a pseudogroup is vaguely a sheaf here. I don't know how precise you can make the analogy. I should look into it. But you'll remember there were some sheaf theoretic conditions earlier on a pseudogroup, the last two conditions. So in essence, our idea is that we're going to take our pseudogroup we formed, we're going to take germs, and that will give us a groupoid. And then if you know anything about groupoids, you'll know you can localize them at certain points to give groups. A groupoid is kind of like a group, but stuck at a lot of points. So the classical example of a groupoid is the fundamental groupoid. You remember a fundamental group is localized at one point. Loops have to come back. But a fundamental groupoid can have, you can first consider the groupoid over all points, and then it's just the path between any 2 points. Or you can localize it at finitely many points. So it could be paths that take you from one of the finitely many points in your set to another of the finitely many points in the set, including coming back to itself. So like we could take a groupoid at these 3 points, and then we could consider loops going like here, paths, not loops, paths going from there to there, or here to here, or here to here, or here to itself. So in the case of finitely many points, it will be like this graph of all the possible paths, and then it's up to homotopy classes. So if there's some topology, it'll be all the ways to go around the topology. When you get a group, it's when you take it just be localized at a single point. Formally speaking, a group is a groupoid with one element, because when you talk about this categorically speaking, the group contained in a groupoid is really its group of morphisms, so it's a little bit of weirdness to pass between one to another. But you can just kind of think, I like to think of it as this localization idea. So now, in order to do this idea, we're going to need to prove something about germs. So as a warm-up to that, let S be a path from a point x to y in our manifold. So here's a point x, here's a point y. We're going to chop this path into a lot of pieces. So we're going to chop it, I don't know, here, 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 and here. And then along each of those pieces, we want to take a product chart. So I think of it kind of as like just choosing a bunch of tiny product charts that cover our path. And what we want to do is choose, along these product charts, we want them to intersect pairwise non-trivially so that we can form a Plaque chain. Contained in this union of product charts is a Plaque chain that takes us from the point x to the point y. That, again, should just be like locally it looks like the leaf. But, again, our portions of leaves we could have, like if we're looking at a top-down picture of what's going on, maybe this is a leaf, and we're going from x to y. Our plaques have to glue together, but maybe our plaques maybe we could take the plaques that go along like the right side here, or plaques that go along the left side. And all of these need to, they glue together to form a leaf as we go between all of the product neighborhoods. But that's only when we consider all of the product neighborhoods that we get a leaf. So there is a bit of nuance locally happening. Again, I know I'm being a little loose on details here. You can check the book if you want all the formalities, but that's the idea. So when we have a plaque chain, it is said to cover S if it's induced from a sequence of product charts covering a path like the above. And then when we have two different plaque chains covering a path S, well, okay, it might be that they define slightly different holonomy when we pass two germs. That would be a concern we'd have. Where these things could diverge apart, and so there might be some concern we'd have. I drew one of these in orange and one in green. I'm kind of cheating here because really we actually start by choosing transversals for holonomy. And a choice of transversals kind of fixes what our starting and ending plaques are, and thus our starting and ending charts. So really, around where I've circled, it needs to be the same two charts to start and end, but in between, our charts could diverge. As long as we get paths of product charts that contain our path in their union, we can take any union we want. So we could even take some of these and we could shift them up or down, and that's okay. Because if you remember how our overlaps work, if we're considering like a point W going to a point Z there, there is a lot of wiggle room within this box here, where we can wiggle up our charts up or down and still have it pass from one plaque to another. So like we have this much height here that we can move, say, our top chart up. Or I guess it's actually half of this. We can only move it up however much room W has. So we have this amount of room right here. And we can move our top chart up by just a little bit, and we'll get some new point, say W prime, when we shift it up. It's still our point. Okay, let's say this a different way. When we shift W up, what will happen is it will give us actually a new point Z, is what I should say. So if we shift W up, we'll get a point Z prime that will come from taking the slightly shifted up copy of W and falling along to the right to get Z prime. But that's still okay. We're still lying in the same two charts. So as long as we found some magical way for our plaques to line up, do our choice of trivializations, such that we could then go from Z prime over to what our final point is. Say maybe this was happening in between, and we had our final point, let's call it X. Maybe it could be that we could go to Z prime, but still pass over to X by a different choice of trivialization. That can happen. It's kind of in case I'm confusing you, which is very reasonable because this is a bit confusing, I think the picture is kind of like this, where we could have some starting point X, some ending point Y, and we could follow it along in a way such that it kind of goes to the left or it goes to the right. And either of those are fine. It's just if we go along to the left side, our trivialization we need to choose is the one that's happening here, whereas if we go on the right, it's the trivialization happening here. So, a priori, different plaque chains can actually define different holonomy, because they're happening at different places on our leaf. We're taking different portions of our leaf to get to the same endpoint. But, even though they might define different holonomy, what we would hope is that they define the same germ of the holonomy. The germ is infinitesimally happening around whatever we care about. So if we look at our path here, you can think of this as saying the germ of our holonomy. Sorry, whenever I undo it, it moves the screen. You can think of it as saying, like, look at really tiny box neighborhoods just centered around our path and take them smaller and smaller and refine them so that they're barely just bigger than the path. And if you take them tiny, tiny, tinier to get the full germ, hopefully the holonomy is well defined then. Whereas if we take really big product charts to define our paths, maybe they'll see very radically different parts of the leaf, and maybe different parts of the leaf could have different, they could see different, because remember, holonomy is saying how our nearby leaves, like above or below our given leaf, how are they pulling apart? Maybe if we're not considering the germ, we could go to very different parts of our leaf, and maybe to the left side of our leaf, the leaves above it are pulling away. Maybe on the right side of our leaf, they're coming towards it. So our holonomy might look different. But if we consider the germ, that problem goes away. My audio was cutting out there for a second. So to reiterate, there are three different things that could go wrong. We have a choice of plaque chain. I guess that's actually second, because our first choice is how to cut up S, and then our third choice is our choice of S itself. So for the first two, you can show it is invariant under them by just looking at a co-cycle condition. And you run through a calculation. It's kind of like when you prove independence of, in a vector space, when you choose a basis, the dimension of the space doesn't depend on like the choice of basis. It's a very similar interchange argument you use, but I think it's somewhat rote. So I'd recommend you check it out, but it's not too important to go through the details right now in this video, I mean. What is important to go through the details of, and what's more interesting, is that we can kind of make it independent of our choice of S. And in fact, the germ ends up being invariant under homotopy of our path relative to the endpoints. So that means that if we have our path S here, we can choose, that goes from X to Y. We can choose another path X to Y, say S prime. And as long as we don't pass through any topology like some holes in our manifold, as long as there's a homotopy between them, the germ stays the same. So how do we prove this? Well, the idea is that given a plaque chain covering our path, a small perturbation, S prime, is still covered by the plaque chain. And remember, so this has to be a really tiny perturbation. So we imagine we're taking a very small one. So we take our homotopy, which could be a very large perturbation, and we split it into a bunch of tiny perturbations. A homotopy takes you from like time equals 0 to time equals 1. This is where it starts, and this is where it ends. But we're going to break this up into like a lot of epsilon-sized time intervals. And for each of those, remember that within two adjacent charts, when we have a plaque chain of length 2, our holonomy was independent of our choice of path. For any path that lied in the union of those two plaques, we said the holonomy of that path was the transition map. And when you have a longer plaque chain, it's just a sequence of that, so you might need to take like even smaller perturbations, but there's only finitely many. So choose a small enough perturbation. Because our path is compact, we can always choose finitely many product neighborhoods to make this happen. We choose small enough perturbations to where we stay within the same plaque chain when we do a perturbation. And we just iterate on that. You just keep doing perturbation, 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 and we're good. Okay, there's a caveat here. Because for a small enough perturbation, fine, we're still in the same plaque chain. But when we do a lot of small perturbations, we'll eventually have to get outside of our plaque chain because it is, a lot of small perturbations glue together to become a larger perturbation. So to be a little bit more formal on this argument, what we're really saying is that our germ is locally constant in time. As we take small perturbations in time, it's locally constant. And since a homotopy goes from time equals 0 to time equals 1, it's a map of that, and that's connected. Well, something locally constant on a connected set, it's constant. So our germ itself is constant. Okay, so what have we done? We have proved, this is taken from the other lecture, that given any 2 points in our manifold, that lie on the same leaf, they need to lie on the same leaf so we can talk about Plaque chains between them. So some points x and y. Any path between x and y. Really, we're thinking of like the homotopy class of x and of the path s, because we can move it around rel endpoints. Any of these paths give us a germ of holonomy. That's exactly what h hat sub s is. It is a germ of a holonomy transformation in our pseudogroup. And what is a holonomy transformation? Well, it's just a partial self-homomorphism of S. There should be the word partial in here. You can get rid of the word partial here, I guess, because we're working with germs. So around, technical stuff. But because it's happening in infinitesimal neighborhood, it's like we're compressing down the domains and compressing the codomains. Because remember, we need the fibers to go forward and backward in time. But as long as the germ, the germ is happening in infinitesimal neighborhood, so it should be contained in all of the compressions of the domains and codomains. So you don't need to worry about adding the word partial there, I think. But you can think of it the same way before, as like partial self-homomorphisms. So we're taking germs of partial self-homomorphisms, and those form a groupoid, and any path we get gives us one of these holonomy transformations. So it is exactly this map here that we've constructed in the above. And it is the fundamental groupoid because it is homotopy independent rel endpoints. And we need an action for it to be a groupoid. It's induced by the theorem above, but to be very explicit, our groupoid action is induced by composition in our pseudogroup. So this is a map from a fundamental groupoid to a groupoid of germs of self-homomorphisms of our total transversal. But we really want to work with fundamental groups, not groupoids. So what we do is we fix a point P on our leaf on a given transversal, and then we consider loops. So we're now working with the fundamental group. So actual loops that go from our point P, stay on our leaf, and come back around to our same point P. And when we do that, we, under the exact same map as before, that then takes the fundamental group of our leaf with base point, our given point, that should be P. I guess I chose X here, so let's a couple times, let's call this X. It takes our fundamental group of our leaf at the point X to the holonomy group of our leaf at X, which is exactly like the image. So our holonomy group of the leaf L at X, which we know H sub X of L, is exactly the image of our fundamental group under the localization of the map above. So it will be some quotient. It'll be some like localization of the groupoid of germs of self-homomorphisms of S. It's a little hard to define precisely. Because again, it happens like in the morphisms of this groupoid. But I think a little bit more concretely, our domain of this map was the fundamental groupoid before, up here. And then when we localize that to become the fundamental group, our holonomy group is just whatever the image is of the fundamental group. So there, you'll hear about the holonomy groupoid, which is the image of the fundamental groupoid, and you'll hear of the holonomy group, which is the image of the fundamental group. Yeah. Or, okay, let me be a bit more precise. It's the codomain of this map, not the image. The image can be a little bit... there's some nuance here with the image in that you might want to talk about the monodromy groupoid and the monodromy group. So we might need to distinguish between the codomains and the images of these groups. Often that is suppressed. It's not an important distinction in a lot of what we're going to care about, but you should be aware there is a distinction here. And again, we don't need to, as a final thing, we're going back to this holonomy group for our leaf. I wrote it with a point X, but because our leaves are, at least if we work with connected leaves, we work with a connected manifold with connected foliations, we can then just talk about the holonomy group of a leaf because everything's conjugate under moving base points around. So our holonomy group becomes conjugate under the homomorphism. Okay, we're right around the hour mark, so hopefully this cleared up some confusions people might have had on some details on the underpinnings of foliations or holonomy. If you have any further questions, please talk to me. You can just ask me in the physical lectures we're having, and I can hopefully address those questions.